Hello again, welcome back. Today we're going to look at the loadings small bridges are designed to carry. There are standards for bridges. Bridges which comply with all the standards are called compliant bridges. The vast majority of bridges, particularly small ones in the UK, do not comply with these standards. When we provide a new bridge, should we provide a compliant bridge? In an increasingly claims-driven litigious society, do we have any choice? It's entirely appropriate for a structure such as the M25 crossing the Thames at Dartford is tightly controlled to ensure it meets all its design objectives. There's a detailed process for managing the design and manufacturing process for structures of this kind. This is the Department of Transport approval process for highway structures. An agreement in principle, an AIP, is produced which specifies every aspect of the project, and this refers to agreed standards for every task. This document can be several volumes thick. Unfortunately, this is the only recognised process for managing the provision of a bridge. It's totally inappropriate for the provision of an 8 metre by 1.2 foot bridge over a small stream on a local footpath. When smaller bridges need to be specified, it's difficult to do this, and this leads to many difficulties. We once received an AIP relating to a 4 metre long footbridge on a public footpath. It's sensible to use some of the standards, but it's demanding to agree which ones are appropriate. This is particularly difficult if your client is not technical. For example, boreholes are sunk and samples taken and analysed routinely if a road bridge is being designed. This information is used to design the foundations. If this was done on most small bridges, it would make them totally unaffordable. It's generally agreed that the design load of 5 kilonewtons a square metre is used for the deck loading on most small bridges. An additional localiser load is used on bridleway bridges. These units mean little to most people who are not engineers. It's approximately half a tonne a square yard. Half a tonne a square yard? This seems rather a lot, until we recognise the 500mm deep snow turned to ice would apply exactly this sort of load. This load is not the load that would lead to the bridge failing. It's the load that would cause deflection more than the agreed limit. If this load was applied, then removed, the bridge would return to its original condition, undamaged. Some bridge manufacturers use this as a reason to use shallower beams than would be required to meet the deflection criteria. This gives them a cost advantage over the more conservative, correct suppliers. These bridges are not unsafe, but they don't fully comply with Eurocode. One can imagine a court scene where a barrister asks, "And was the bridge compliant?" And the answer is, "No, not fully." Most bridges have parapets. These are to stop people falling off the bridge. In order to comply with the bridge code, they need to stand up to crowd loadings. These loadings define the size and spacing of the parapet posts and the arrangements for attaching the posts to the beams. We'll return to this when we look in more detail at parapets later in the series. To summarise, pedestrian, cycleway and bridleway bridges have a design live load of 5 kilonewtons a square metre. Bridleway bridges have an additional localised load to take account of a horse rising up on its back legs. The design loads for small vehicle bridges are more demanding, and we will deal with these later in the series. We will deal with the foundation loadings when we look at foundations. We recently designed a bridge for a rhino enclosure at a zoo. We speculated if a rhino was physiologically able to rise up on its back legs, and if it did so, what the localised loadings would be. We're managing to keep your attention, and you'd like to see some more of these posts. If you like the posts, please subscribe to them and tell your mates. Thanks very much. See you soon. Bye.